let's continue with the last lecture. And in the last week, we tried to introduce the types of the Hawaiian antennas, which is composed by two kinds. All right, the first kind is based on the conductive currents and supplying the dipole antennas or the wire antennas. And the second type is based on the aperture, so that has the Hawaiian antennas, the Cascade antennas. And so now for this lecture, we try to introduce the radiation by the aperture antennas. We would try to concentrate on its radiation pattern, its antenna gain, and also the controlling of its radiation pattern, and also finally the antenna array, which is composed by several identical antennas by controlling its magnitude and by its phase, and can achieve the shape of the final beam pattern, and also the radiations near the beam direction of this radiation. So, firstly, we will introduce the radiation by large aperture antennas. So for the wire antennas, as we mentioned previously, its radiation is based on a method that we separate as to be infinitesimal elements, right? And each element can be regarded as an isotropic antenna. And then after that, we take a sum or the integration of all these points. All these forms to get the radiation pattern by the whole wire antenna. So this is for the wire antennas. For the large aperture antennas, the most typical of that should be the Hawaiian antenna. So for Hawaiian, let's plot a typical side of the Hawaiian antenna. Right, the paramount Hawaiian antenna. It's all right. So this side is a transmission line. This side is a transmission line, and here is the whole part, the main body part. So first is when there is a source, right? So how it connected to the antenna? It's connected by a coaxial transmission line. Right, and for the coaxial transmission line, its outer side part is connected to the metal body of this waveguide, and the inner part connects to the waveguide inside of this part through a small hole here. So it achieves the coax to the waveguide. And inside of the waveguide, the point of this cable or the transmission line can act as a monopole, and it's going to radiate the electromagnetic waves to this waveguide here. And inside of the waveguide, it propagates to the hole and then radiates inside of this actor. And then it launches out into the free space here. So in this lecture, we just try to analyze the electromagnetic waves which propagates from the surface, the aperture, that's the aperture, and into free space. Okay, from the aperture into free space, and it propagates in free space. It propagates in free space, and it has its own spacefront, right? And this spacefront closer to the antenna should be more like a sphere, and farther away it can become a little bit flatter, and then finally we can regard it as a planar. So the electric field of the wave arriving at the aperture, it can vary as a function, alright? The electric field on the plane of the aperture, it cannot be a constant usually. It has a distribution, and we can regard it as plot as a Cartesian coordinate system, and put it x axis, and y axis. Okay, here is x axis and y axis, and along this direction is the theta axis, which directs to the propagation of the electromagnetic waves. And because this is just the Cartesian coordinate system with respect to the aperture, so we use x-axis as xa, y-axis as ya, and theta-axis as theta here. So that means the electric field on the plane of the aperture, it can be expressed as, we use EA, okay? XA, YA, alright? And there's no theta A, alright? Because theta A is always equal to 0. So we can express it as this one, and it is called the electric field aperture distribution. So finally, what we want to do is we analyze how to express this parameter and get the total radiation pattern by integration of this electric field over the whole aperture. So now we really express the electric field by Maxwell's equation, alright? As we demonstrated previously in the electromagnetic field. A wave. So Maxwell's equations to get the solution of the electric field. It is expressed in vector form, alright? So it considers the propagation direction of the electromagnetic waves, and also as polarizations, and many other parameters or the conditions. Another one is the for a simplification, as we consider a scalar form. Right? We use scalar form. That means it can simplify our calculation. And the scalar form, we call it Kirchhoff's approximation. So we can express all these values via scalar form, and it helps us to get to simplify the calculations of the expressions here. And another thing we need to consider is for the aperture. For example, if its length along the x-axis can be already expressed as Lx, and its length along the y-axis, it can be expressed as Ly. So it's after the aperture area, all right? And as we when we try to calculate the directivity and the antenna gain, we usually consider as effective aperture and also as physical aperture, all right? So the physical aperture can be expressed as Lx plus Ly, okay? And as we mentioned here, the radiation by a large aperture antenna. So large aperture, that means its size or its dimension, Lx or Ly, should be larger than several wavelengths. So we call it a large aperture. And for example, if you take a look at the antennas that operate in your system, for example, for the terahertz range of 100 gigahertz, 110 to 170 gigahertz, its antenna size or the aperture size is around 1 centimeter. However, its wavelength is around 3 millimeter, 2 to 3 millimeter. Yeah. So it should be several wavelengths like that. So this is called, it is called the large aperture size. And here we just more concentrate on the large aperture antenna. And also we take another condition is that the observation point Q is far away from the aperture, and it should be in a far field region, right? Far field region. So can you remember how the far field region is defined? Should be larger than 2d squared divided by lambda, alright? D is the size or the dimension of the aperture, and the lambda is the wavelength. So R is the distance between the aperture and the observation point. So now we can express the electric field. So we usually firstly express the electric field E. As we mentioned previously, it should be the total electric field observed at the point Q, for example. It's related to the radian, elevation angle, and the azimuth angle, right? Like this one. Okay. And as expression as spherical angle, spherical wave. This term, all right, is inversely proportional to the distance between both points, and also it represents its propagation direction. The minus means it propagates along the positive beta axis, all right? And if this is plus, then it should be propagates opposite to the beta axis. And also, we have the term as here. This side mostly defines as amplitude, all right? And we should have its distribution. So this one is called a form factor. It's related to theta and phi, right? So here is J divided by lambda. So this is a general expression for the electric field at an observation point theta Q. So here is this angle should be the elevation angle, right? At the x or y Cartesian coordinate system, and so this is the expression. And then how we get the expressions for the h theta phi. So for h theta phi, it has its own expression. I will not sure how to obtain that to save the time. h theta phi it has its own expression as h theta phi. Of course, equals what? Equals the expression based on the electric field. It should be expressed by A, X A, Y A, expression of H, and the integration over the whole H, right, from minus infinity to positive infinity, and also it has an exponential part. Jackie. XA crucify plus YA simplify. As we mentioned previously, the form factor here, it depends only on theta and phi, right? It does not depend on its position or its the x-axis and the y-axis. So we take integration of each with respect to dxa and dya here. So now we put the expression here, and we can get the expressions for the electric field at the observation point. And then what we can do is we can calculate the electric field, and also we can get the power density. All right. So the power density S R theta phi equals absolute value E R theta phi square, right? Divided by 2 eta node as the expression of power equation like that one. And so it can further be expressed as the integration of this part to eta node lambda square r square, this part disappears, h theta phi square. Alright? So this is the expression for this part and the power density. So this is just a general form for the expressions of the electric field and the power density. And now we want to take some two kinds of typical antennas for an example to show how to calculate the electric field and the power density. So firstly, let's take the rectangular aperture as an example. For rectangular aperture, and we can plot it by a square. Okay, rectangular aperture, and we put a Cartesian coordinate system inside of it. So this is the explanation for today. This is XA. This is YA, right? And on the side, theta A. Okay. So at this point, we have an observation planar. Okay. and the observation planar, it has its own coordinate system, x and y, okay, and then 0, theta here, okay. So now if we have a position ex and ea, for example, we have ex and ea. An area element is length, this side is dya. Here is dxa, okay, at position xa and ya. And this unit area here. So if we have an observation point q, so the distance between this point to the observation point q, the name is s. From the origin to q, we call it r, okay? And here it should be the elevation angle theta. And now we have the from the x-axis, the shadow, this side is should be what? Angle should be what? The shadow on x or y plane, the angle with respect to the x-axis should be continuous angle theta, phi, alright? So now we can express the electric field at the unit area. Firstly, we have an assumption that the electric field over the whole aperture should be uniform. That means they have the identical electric field values, the values of the electric field. So we can express the electric field EA, XA, YA equal to E naught. So that means it is uniform over the whole aperture. However, if it is outside of the aperture, so we take it to be 0, right? So we have condition here. So this length is Ly. This length, we name it Lx. So that means it equals E naught when x is larger than minus half Lx, smaller than half Lx, and Ya larger than minus half Ly, smaller than half Ly. So it equals 0 at other conditions. Okay, so this is the distribution of the electric field. Then we come back to the expression by this equation. Then we can calculate the form factor h theta phi. Alright, so we'll get the form factor, the expression for the form factor h theta phi. It can be expressed as the integration of that one, and EA becomes E naught. So here x minus j k, no minus sin theta cosine phi theta xa cosine phi plus ya sin phi, right? And then dxa dya, and because it has values only inside of the actual, so it becomes minus x half Lx minus half Ly half Ly here. So this is the final expressions for the form factor here. And if we just look at this expression, you can see it looks like it's not very difficult for the integration calculation. All right. So we just take the expressions for this part, figures, and for this part, the exponential part. We just an exponential function or term, we just take the integration of it. It's not very difficult. And also, we have another form of method to do the calculations. We just do the variable transform. All right. So, for example, we can express a new vector u. We can express that k sin theta cosine phi, and name of v equals k sin theta sin phi. So then, this term can be expressed as, I would neglect the expressions for this part, and the a node is constant. All right, so it can be outside of the integration. E j u x d x a e j with y a d y a. So expression by this term, and then we can do further the calculations on it, and the final solution of it. To express it, I will not show you the process. Okay, and I hope you can do this by homework. So the final expression of h theta phi can be expressed as j e a p lambda, and also the spherical term k r divided by r times sinc phi Lx or lambda sin theta cosine phi, and sin pi Ly divided by lambda sin theta sin phi. So this term here, the AP, as we mentioned previously, it equals Lx times Ly. All right. So this is the final expressions for the form factor. The sinc function, the sinc part, for example, sinc t, for example, it equals sin t divided by t. All right, the expression, and when it has a property as when t equals to tends to 0, then sinc t tends to how much? 1, yeah. Tends to 1 here. So this is going to be used later. Just a short review. And the expressions as we mentioned previously for the power density of H. So the power density, where is the power density here? The expressions for the power density is like this one, right? So we get the H theta phi form factor, we can calculate it. So the power density as R theta phi can be expressed as let me come back to eta node. To eta node lambda square r square absolute square h theta phi. Alright, so the this part, the real part can be taken out. E node square AP square and 2 meter node lambda fourth r square. Alright, then the integration and the absolute value of this part should be equal to 1. Right, so we have only the sink square times sink square. Alright, this from this sink here. Okay, so we get the final expressions on this one. Now we want us to say the expressions at the in the plane of x, o, theta, for example. So we come to here. The plane x, o, theta. This plane, that means the phi, the hypotenuse angle always equal to 0. Alright? So it's that in this plane phi equals 0 always. So that means phi equals 0, sin phi equal to 0. So that means when t towards to 0, sin 0 equals 1. So this term equals 1, and just delete it. And phi equals 0, so it's not dependent on the phi here. So the expression finally at this one here. And now sin r theta can be expressed as the maximum and magnitude times sec square pi Lx lambda sin theta cosine phi, because phi is 0, cosine phi equals 1. Alright, so this is the power density in the x o theta plane. So we get the power density now, and I wanted to say how the beam pattern is gonna look like in the x o theta plane. All right, when we try to say the beam pattern in the Cartesian coordinate system, a two-dimensional Cartesian coordinate system, we take a shadow. We take a shadow on the x o theta plane or the y o theta plane. All right. So firstly, we just say the x o theta plane. So the as we mentioned previously, mentioned this here in this course. There is, to say the beam pattern, there is parameter. It is called normalized radiation pattern. The parameter of it, or the radiation intensity, we call it f theta, because it is not dependent on the phi. All right, because it is in the x o theta plane, and it is not dependent on the distance between both between the source and the observation point. So f theta, it is expressed as the power density divided by the maximum of the power density, and so the maximum of the power density should be the magnitude, right, the nth node. So that means this term divided by the nth node, we have only the sink function, the square of it. So that means it can be expressed as this term, pi Lx over lambda times sin theta. So this is a general expression for the radiation pattern of an antenna by this form. So now that means usually if we wanted to analyze the radiation by an antenna pattern, if we have if we do not have the exact parameters of its dimension or its radiation pattern, we usually use a sinc function to represent that. All right. So here you can see that it's better if we can use a square of the sinc function to represent a general radiation pattern by a whole antenna. So this is the expressions here. This one, and based on this form, we can plot the radiation pattern or the normalized radiation pattern. So let me plot it, just a hand plotting. So it's not exactly like that. I just wanted to use it to express some other parameters based on H. So here is the radiation pattern, and this is amplitude or S F, okay, in dB. So because it is normalized, that means its maximum should be 0, right? So 0 dB. It looks like. This form, okay? And this form. This form. And this form. This form. Okay? Just a simple plotting. And so let's come back to this one. So the variable here should be pi Lx over lambda times sin theta, right? So we name it as let gamma equals pi Lx divided by lambda times sin theta. So the radiation pattern F gamma becomes sin square pi gamma. That's this one. Okay, so I will come back to here. So the x-axis should be gamma, the y-axis should be F gamma. This one. So when we get the beam pattern, what we really want to obtain the first thing should be the beam pattern of the main lobe. Alright, so here is the main lobe, that what we usually used or we really want to employ the main lobe. And all the others should be side lobes, alright? This one also side lobes. Here. The first thing. The second thing, the first thing should be we wanted to put the main lobe much higher than the side lobes, alright? Then we can get a much smaller or reduce the interference by other side lobes, especially for the detections and also for the communications. It's also the same thing. So the second thing is the beam width. All right. Second thing is beam width. So for the beam width, we already use because it is at the x or theta plane, so we call it beta x or theta. It should be expressed as the beam width, or it can also be called half power beam width. That means half power beam width, that means when F gamma becomes half of it, right, corresponds to that one. So half 0 dB. So the half of it comes to how much? Half, corresponding in the decibel scale, corresponds to 3 dB, alright? So reduced to half of H, so that means it reduced to minus 3 dB right here. So now from here we get the beam width. So at this side, that corresponds to the angle. The gamma equals Lx or lambda times sin theta, alright? So this is gamma 1. This side corresponds to gamma 2, alright? With gamma 1 we can get an angle theta 1. Gamma 2 we can get an angle theta 2. So the beam width equals theta 2 minus theta 1. We can get the beam width here. And here, because it is symmetric with respect to this one, alright? So it can be expressed as 2 times theta 2 when theta 1 equals minus theta 2, alright? So then when this one equals half, then we can calculate it as sin square pi Lx over lambda sin theta 2 equals half. And then that means pi Lx over lambda sin theta 2 equals 9. So based on this equation, we can get the expressions, and sin theta 2 equals lambda over Lx times 0.44. Okay. So this is based on this. Let me note the wavelength, the operating wavelength, and the dimension of the square aperture. Then we can get all the rectangular aperture. We can calculate it. So usually, as we mentioned previously, the aperture for the large aperture antenna, that means its dimension should be several of the should equal to several of the wavelengths. That means lambda is much smaller than Lx. So when lambda much smaller than Lx, that means sin theta 2 much smaller than 1. Alright? So that means sin theta 2 can equal roughly to theta 2. So beta x theta can be expressed as beta theta 2 can be expressed as 2 times sin theta 2 cos 4 h lambda over Lx. So based on this expression, even though we do not take the measurement on the half power beam width of the angle, we can calculate it roughly by this expression. When we buy an antenna, we know this operating frequency lambda, and we can measure its dimension, right, by using a caliper, for example. Then we can calculate, get the rough values of its beam width, beta x theta here. Okay, now let's take a short break, and we're going to come back 5 minutes later. So now we get the beam width for the main lobe, and further, if we wanted to, for example, we wanted to reduce the side lobe and keep all energy inside of the main lobe, alright? And so as get higher directivity or higher antenna gain, for example. And what we should do? So we already need to change the shape of the antenna aperture, and so for example, if we wanted to, for example, if we have a circular beam pattern, for example, or we have let me think, yeah, not circular. For example, we have still a square. Yes, still a square. Yes. This one. So it has the beam pattern, a three-dimensional beam pattern, right? So this color. The first beam pattern is along this line, right? Along the this is the y-axis. This is the theta axis or x-axis. So in the O theta axis, and has three-dimensional. Not sure how to plot it like this one, but I like this one. So if Lx equals Ly are identical to each other, for example, as we beta. So as we mentioned previously here, beta x theta equals beta x theta equals 188 Lx divided by lambda divided by Lx. Lambda divided by Lx. Lambda divided by Lx. So if, and this is beta x theta, beta y theta equals lambda by L1. So if we wanted to increase beta x theta, that means decrease the beam width. We can increase Lx, right? Increase the aperture size. The same thing. decrease beta, while theta decrease the beam width, beta increase Ly. So increase the aperture dimension, we can reduce the beam width of the beams, and also it gives us another performance as the side lobe is going to be suppressed. Suppressed by it. So this is for the expressions for the electric field, and also there is another thing here. We take it as 0.88 the parameter. All right. So actually, if for a general expressions for the beam width of antenna, this is just for the rectangular antennas. For typical antennas, the whole antenna also can be expressed as kx, for example, the x theta, kx times lambda or Lx. Kx is just a parameter, a constant related to the stiffness of the taper, for example, if there is taper, for example, and it can be equals, it ranges between the two kinds of values. So the first common value is 2, the maximum is 2, and the smallest is 0.88. So in this range. So when we increase the dimension of the rectangular or the aperture, we can increase the beam width, also can change. If we also decrease the beam the second thing is, if we change the constant kx, the kx relates to the shape of the aperture. For example, we have aperture, erase it. Previously it is flat, alright? So if I want to plot it not flat, tapered. Aperture, that means it's this kx gonna be ranges in the range of 1 to 2 here, and so it's gonna keep the beam width much wider than this condition in this dimension, in the x or theta plane. So this because this is due to the shape of the aperture and also its dimension of the aperture. It's going to affect the radiation pattern of the antennas. Another thing that we wanted to introduce is directivity, all right? Directivity D, capital D, is related to the antenna gain, right? By divided by an efficiency parameter eta, all right? So the aperture D is related to 4 pi divided by azimuth angle times the elevation angle, alright? So the azimuth angle and elevation angle here is represented by the beam width x theta, beta, x theta, beta, y theta here, because the AP, the physical aperture, equals beta x theta, Lx times Ly here. And so it can be Lx and Ly. So the beta x theta can be expressed by this form here, right? And this is 0.88 88. So it's roughly equal to lambda over Lx, beta y theta equals lambda over Ly. So this expression can be expressed as 4 pi Lx Ly divided by lambda squared. So it can be expressed as 4 pi AP divided by lambda squared. So that means now, when we know the dimension of the antenna, and also its operating frequency or wavelength, we can calculate the directivity of it. Alright? And then we can calculate its antenna gain here. And also, if we know the dimension of the wavelength, we can calculate its beam width. So we do not need to take measurements in that room. For example, we do not take measurements by using the A, and we can just get the values by calculation. And even though it's not exactly as the actual device, because it also depends on the manufacturing process, right? If it has now some solid device, or the errors in the fabrication, and so we can just using these two equations or these two formulas to obtain a rough expression for that values here. So this is for a square or a rectangular actor, as we mentioned here. Rectangular actor, all right. So if we have rectangular actor, and also we have some like the circular actor, right? For circular actor, it looks like a cylinder, like this one, right? For circular actor, the hole looks like this way, right? So we want to put another system again. YP XA theta P. Alright. The first thing is, previously we used XA and YA DA as XA and YA to express the electric field in the plane of the actor. Here we wanted to express it as a pole system. We use RA, right? And YA to represent that. Alright? So that means XA equals RA cosine YA. YA equals RA YA. Alright? So the form factor H theta phi, the form factor, can be expressed as the XA divided A becomes EA RA, and exponential minus j K RA sin theta cosine phi A plus sin phi A times RA d phi A. Okay, and RA is from 0 to capital R, and R as the radius, the radius related to, all right, and phi is from 0 to pi. And the solution of it, I will not to show you the exact values of it, but I'll just show you the final solutions to pi, 0 to pi, into A, R8, and J node, K, R8, sin theta, R8, dR8. So J node here, this term J node is the 0th Bessel function. So based on those equations, we can also get its half power beamwidth, which half here. When this term equals the, we may get is the normalized radiation pattern. So it is equals pi by lambda over A. Sorry, it's radius here. It's A. So this is the expression for the circular actor, and when the electric field is normalized. So I have H and this for the rectangle and the circular actor now. And after that, what we want to do is we want to introduce the when we have several antennas work together and they are positioned as an array. So for the antenna array. So the elements, they have several identical elements, right? This can be dipoles, slots, Hall antennas, and also the parabolic dishes, like the cascading antennas. And the desired shape of the far field radiation, it can be controlled by controlling the amplitude, the radiation amplitude, and the phase of each element. And we can get what we want, the desired the beam pattern. So now, if we have several elements, so for example, 1 element, 2 element, second, third, many, and last 2 elements, so like this one, and for each one, so we name each as the 0th first, then -3, -1, and -1. That means we have n elements. Okay. For each element, it has its the phase shift right. Also, it has an amplifier or attenuator. So this is psi -1. This one is n -1. Also this side, the same thing. For each element, it has a phase, connects to a phase shifter and an amplifier or attenuator. Mostly amplifier. Psi 0. a node next to this term. Okay. Now we should concentrate on the just one element firstly. So, for example, we have the an observation point. For example, it is positioned at Q, and its position as our node theta phi. Okay, because we set the Cartesian coordinate system. This one is along the y-axis, and this side is along the z-axis. Okay. Now, our node, that means the zeroth element is positioned at the origin, and the distance between this point to here, okay, is our node, all right? And this point to here is named as R1. Finally, this point. Sine to it should be Rn minus 1. So we can get the expression for the electric field from the ith component. Its distance is Ri, right? Theta and phi. It can be expressed as what kind of form it should looks like. Let me come back to the expression. Oh, I erased it. Okay, no problem. Let's rewrite it. So it has a spherical component R, y, e minus j, k, r I. Alright, and also its shape is determined by another element. We call it. It has its own name. Is related to the beam pattern of the antennas, so we use it as Fe, theta, phi. It has no I because we assume the antennas are identical to each other, so their radiation pattern should be identical to each other. And as we see here, it has amplitude controlling on the amplitude at the face and amplitude here, so we use capital AI to represent it. So AI is related to the amplitude by the amplifier and the phase control here. So they're related to this one. So this is the expression, a general expression for the electric field of each element. So we wanted to get the total or the final beam pattern. We want to calculate, we should calculate E, R node, theta, phi, equals the sum of all these components. Alright, I equals 0 to capital N minus 1. Alright, we add them together at this point. Alright, so it can be expressed as sigma I equals 0 to capital N minus 1, and we have AI, we have Ri, E minus J, K, R, I, alright, and also Fe theta phi. However, as we mentioned previously, this is identical for all the elements. So that means this can be taken out from the summation. Okay, now we get the expression here, and we want further to simplify it. So the first thing we wanted to do is we wanted to get an expression for the electric field. So first thing, let's look at the this point. So okay, here, this one is the from y-axis, theta axis. So this angle is elevation angle, all right, theta, because it's the length of the array is much smaller than the distance r. So all the angles we can call it theta angle, for example, here. And so now we know our node. How about if I want to get R1? So it means our node minus this point part, alright? This R1 equals our node minus this part, alright? So this part equals this length. This length is the distance between both neighboring elements. We call it d. Okay, this part equals d times cosine theta. Right. So that means our node minus minus d times cosine theta equals r1. Okay, and for the an example for the minus 3. R and minus 3, it equals R node minus this part, right? Minus, change the color. Minus this part, right? So this part, its length equals n minus 3d. Alright, the elements, the total part of all the elements times cosine theta. So n minus 3 times d cosine theta equals this one. So that means Ri, Ri equals R node minus I d cosine theta, right? The expression like this one. So we put this term into this equation, and finally it can be expressed as the form, a more general form. Let me express it. Put it here, and Ri can be represented by this term because d is much smaller than R node, so here it becomes R node here. But this side it has R node, and also another term is this one, J I K D cosine theta, right, times this term. So we can express it as E R theta by expressed as E theta phi. E minus J K R node. Constant, right? I equals 0 to minus 1. AI times E J I K D cosine theta. This term. And then we get the electric field. We want to get the power density R theta phi equals square E R theta phi divided by 2 each node can be expressed as 1/2 each node R square times E theta phi square times this part. I equals 0 to capital N minus 1 E J I K D cosine theta. Oh, I lost E I square. Alright, so this expression. And as what we wanted to totally express is we wanted to express it as an equivalent value for the power density SE R node theta phi times sigma 0 to N minus 1 AI E J I K D cosine theta square, right? So this side, this one is related equals to this part as the maximum of H. So after that we can get the array pattern. The pattern corresponds to the power density divided by the maximum of power density. Alright, like this one. So it can only be expressed as I equals 0 to N minus 1 AI E J I K D cosine theta square. This one. Okay, so now we get the array patterns here. We can take further analysis on the array pattern, and if I wanted to express it more clearly, it can be expressed as beta equals sigma 0 to N minus 1 AI E J psi I J I K D cosine theta square. This one. Okay, and when we control the amplitude, control the phase, we can achieve the control of the final array pattern here. For each element, we can separately controlling for the amplitude and for the phase shift. We can achieve such a calculation on it. So now, if we assume, based on this condition, if we assume we have n elements, so, and we assume all this, we do not want to control their phase shift. So we put the phase shift f phi I equals a constant phi node always. Assume such a condition, and let me rewrite the array factor. So we can put the array factor E J psi node always, alright? So it is constant. Psi equals 0 to n minus capital 1, and ai ej I kd cosine theta square, right? And in the absolute value, this part equals 1, so we only have this term now. And we also wanted to assume constant gamma expressed as kd cosine theta, so then that can be expressed as I equals 0 to n minus 1 ai ji sigma gamma square. This one. So now let's assume if the amplitude is distributed uniformly or uniform amplitude distribution, so that means the I always equal to 1. So the array factor FA gamma equals AI equals 1, alright? So equals when I equals 0, it equals 1. When I equals 1 is J gamma. When I equals 2, EJ 2 gamma, right? EJ and minus 1 gamma square, right? So I think you guys know how to express the expression for inside of it, right? Expression for this one, I'm not sure it should be. Over 2, all right, times should be like this one. So finally, this term equals the square of that. So it equals sin square half n gamma divided by sin gamma over 2 square, like this one. And we get the expressions for the uniforms here and here. So we can see the variation of this array factor with respect to the angle theta, right? The angular distribution, but here it also determines on the distance, d, distance between neighboring elements. So when we change the distance of both elements, it's going to change the shape of the array radiation, all right? Because it changes the array factor here. So for an example, we plot, if we assume usually we set d equals half of a lambda here, and the radiation pattern looks like smaller this one. Just keep it, okay, and what's this one? This one, okay, half of that. This is d over half lambda. If when we increase it, so d equals 3 lambda over 2, the radiation pattern becomes much more complicated. Like this one. So first layer has just only main lobe, all right. But here, besides its main lobe, it has two more lobes, side lobes, which have almost the same amplitude with respect to the main lobe. This is what we do not want, all right. So what we usually do in the antenna array designment is we need to put, because it's 3 times, it has 2 repetitions. So we need to control the distance between both elements d, which is smaller than over 2, lambda over 2. This condition. To achieve, we have only one main lobe here. For sometimes, if we have the conditions that, and we have this both side lobes, it has its own name. It's named as grating lobes. It's grating, right? That means it is what we do not want, but it's generated randomly and expectedly as that. So this is, as we mentioned here, we set the amplitude is uniformly distributed uniformly, and so there should be another condition that the amplitude is not distributed uniformly, right? So it is called as binomial distribution or amplitude distribution. Okay, so that means binomial. That means 二项式，对吧 ？In Chinese. So we assume one condition as ai equals n minus 1, for example, that divided by I that n minus I minus 1 that. So this is amplitude, and finally we can suppress the its side lobes. Under certain conditions, we can suppress its side lobes, but its beam width, no, side lobe, but the beam width becomes much wider. Let me compare it to the previous one here. All right, look at here. Even though it is narrow, but it has side lobes here. But when we use the binomial amplitude distribution, it has its side lobes erased, but its beam width becomes wider. So that means in the antenna design, there is a trade-off relationship between the side lobes and the beam width of the radiation patterns. The beam width of the main lobe. Okay. So here we just use this method to control or to change the amplitude, the shape of the beam pattern. And as we mentioned here previously, the antenna array achieves 2 conditions. The first one is the controlling of the beam the radiation pattern. Another is used to steer the beam. All right, the beam steering. So here we wanted to introduce how the antenna arrays can be used for the beam steering. Okay, so for beam steering, that means previously we set the phase shift to be a constant for each component, all right? So for beam steering, we need to consider the rule of the phase shifters, and we come back to this plot, okay? And we set the psi I equals I times third. Third term means a linear incremental phase delay. So delta is called of phase delay achieved by the phase shifter. Okay. So if we have this form, then let's come back to our previous expressions. This expression can be as we put it as here, okay, for this condition. So AI equals expression of AI times E jet psi, or right, psi equals I delta here. And so this expression can be further expressed as AI times, oh sorry, it's minus AI times E jet I K D cosine theta minus theta. Alright, so the term inside of the bracket. Okay, like this one. Okay, let's take a short break and then come back later.哪一个项目？我都忘了哪一个项目？还是他家的？是60万的吗？是一个，反正是不是有一个？那是不是再往把时横站上去吧？哎呦靠！我一直以为都是已经拖过来了。那我再问一下，它这个是两个项目，它应该是两个方向，两个方向都缺一点。行了，我跟他说一下，行，然后这个的发票借出来了吗？然后还开始借新的是吧？那你说？ will get the new expressions for the array factor here. And the only difference between the previous one is we have a term delta, right? Incremental phase delay. So if I want, we also have an assumption previously that gamma equals k times d times cosine theta for the simplification of expressions, right? So what we wanted to do is we want to express another term here, gamma prime, use it to express k d cosine theta minus delta. So now the fa becomes gamma again. So equals sigma I equals node n minus 1 ai ej I gamma square again, alright, as the previous that we assumed here. And now what we wanted to do is wanted to introduce gamma as a constant, alright, it is phase delay. I'm going to express it as k and d are also constant, right? It's determined by the physical dimension of the antenna array and also by the operating frequency of it. And so cosine theta minus, I want to express delta to be k d cosine theta node, like this one. Okay, why I wanted to express it like this one? Because it's coming from because it's gonna help us to express how the beam steering operates. So, for example, as we plotted previously, the that's the plotted like this one. Okay, here, and this is gamma, right? And here plot the maximum. So its maximum is along this one. The single function square, right? Like this one. This one is probably the same thing. This one, like this one, right? So gamma here, this part is gamma equals what? Gamma equals this, because it's metric. This is gamma equals 0, right? So this is previously for this condition. So when gamma equals 0, that means theta equals 1 over 2, alright? So that's why in our previous plottings, so this is theta equals 90 degree, theta equals 90 degree, theta equals 90 degree here. So, and we call this side as the broad side direction. Okay, broad side direction. That means its directivity is direction. Okay, it's the maximum directivity it can achieve. So this is for theta equals 90 degree, and it is fixed, right? Because k, d are constant. All right, always they cannot change. But here, the same thing. However, for this condition, if we want to change, the broadside direction here, we want to set it to be 0. That means this term equals to 0. All right. So how it can achieve 0? That means theta equals theta 0. All right. Theta node. It's gonna achieve this part. So that means the main beam, the main lobe, directs to theta equals theta node. So when we change, or when we, for the controlling side, when we change theta node, it can be changed from 0 degree, 45 degree, and 90 degree, all right? So the main beam, the main lobe changes from 0 to 90 degrees also. So this is achieves the beam steering. So for such a condition, if we achieve here is theta equals 90 degree, all right, okay. This let me plot another one. Even we can steer the beam, all right, and change the direction of the main lobe, then how it gonna affect the other parts such as beam width and its side lobes gonna also change. They cannot keep fixed because the phase, the change of the phase delay could also change the beam width and also change the side lobes of the beam pattern, not just the beam's the radiation direction. So, for example, this is for theta equals theta node equals 90 degree. Okay, so it's like this one. Theta node equals degrees along this direction, and when it comes to theta node equals 0 degree, let's simplify. It becomes much wider, like this one, much wider. Theta node equals 0 degree. So the beam width was changed due to the beam steering, and this is gonna affect. And when we're trying to design the phase arrays for the beam controlling, we need to take care of this point, and we have some overcoming solutions for that one. For example, we design a two-dimensional antenna array, and to offset this drawback caused by the beam steering, and this is going to be a much more complicated process for that. But what I want to show you guys is just the changing by code. Okay. Let's use the non-uniform. So here is just a constant amplitude, the change of the amplitude for it. So we can see for the constant amplitude, its beam width is much narrower, but it has no more side lobes here. By using the binomial distribution, the side lobes are suppressed, but the beam width becomes much wider, all right? It's almost more than 2 times of the constant amplitude distribution conditions. And so anything, when we try to get the shape of the main lobe as what we wanted, it also gonna lead to the variations of other parameters such as the side lobes and the beam width also, and other parameters. If when we using the dual polarizations, then it's gonna change the ratio of both polarization components also. So this is what I'm going to introduce for this lecture, and for next week we're gonna introduce the interactions of the electromagnetic waves with respect to the atmospheric constituents, such, because this course is for the weather radar, right? All right, the meteorological weather radar, and so we're gonna introduce the topics on the atmospheric particle constituents. So we have, let's see, another thing is not this one. Sorry. Yes. So the homework. So we have one homework, all right? The homework is obtained based on this formation, this formula to obtain the final expression. Where is it? Here. The final expression, this term. Okay. So just mathematical calculations on that one, based on the form factor. All right. We take an integration over the whole aperture and obtain the formula of this part. Okay, just as the homework. After you finished the calculation, based on that, send it to my email account. And the deadline is before next lecture. Okay? So we have, take care, we have the homework for the evolution from this part to this one. Okay? From the 3rd page to the 4th page. And then write it, you can use handwriting or the type that by using the Microsoft Word, and then send the PDF to this email account. Then before next lecture, okay, just 1 week, and I think we're done for this lecture, and I'm gonna see you guys next week.